Welcome to all of you in this new of why we use SLOS ticket tool. So SLOS ticket tool basically used to simulate any semiconductor devices prior to fabrication because if we have to understand the electrical behavior, internal mechanism, everything of the device, so what is the way through which we can understand? This is only one thing by simulating that device. So that simulation part has been performed by a tool that is called TCAT tool. So here I am going to discuss about at least TCAT tool and oh, the code which is writing in the Elastic Cat tool. There is a steps, there is a method, there is a way where you have to on that way we have to write that code. So the way all that way I have discussed here one by one, and what is the steps we have to write the code, that steps I will discuss. And after that theory part, I will give you one code of TFET, basic TFET code, SOI TFET you can say. Uh, and I will simulate that code on Atlas also, and I have to show, I will show your result in current form as well as structure format. So let's begin. Now, here everything written. Atlas is a physically based 2D and 3D dimensional device simulator. So in this tool, we can simulate 2D as well as 3D device. Now, why we do simulation? As I have already told you, it predicts the electrical behavior of a specified semiconductor structure and provides an insight into the internal physics mechanism associated with device operation. All of you know that part? Okay. Now let's begin. What the main motto of this lecture? First one is, before writing the code of Atlas TCAT, we have to write Go Atlas. First point we have to write. Okay. Now, there is five steps basically involved in any code of the Atlas TCAT. First step, we have to define structure specification. Second step, we have to define materials, models, specification. Means what model you will include your physics. Model means nothing but physics. What physics will be involved in your device? That that physics has defined by models. Okay. Now numerical method. So Newton-Raphson method basically we use for solving any electrical parameter. Now solution specification. After getting all the value, we can find log file, solve file, load and save. Now result analysis, we can extract any parameter after that, or we can plot that on Tony plot. So in structure specification, we have to define meshing, region, electrodes, doping. Okay, one by one I will discuss. So don't bother about those things. I will discuss one by one. Now material models contains materials, models, contact, interfaces. Numerical method selection contains what method you want to include and all other things I have discussed. So now let's begin one by one. Now using the command language to define the structure. So what language basically we have to do? As I told you that we have to define the structure. For structure, first part was meshing. What is the meaning of meshing? Let me tell you what is the meaning of meshing first. Suppose you have a structure like this. Sorry for drawing. I am very bad for drawing, so sorry for that. Suppose you have a two-dimensional device like this. So what you will do, you will divide your device in very small unit. Okay, you have to divide your device in small unit. You have to cut device like in x direction and y direction. That is called meshing. Means if this unit part, this is the basic cells of your device. So it what it did, it it divide your device in very small part. Why it is necessary? Because the physics which will apply by simulator only that small part. Okay, and it will get the behavior of charge and what is the movement of charge, everything. It will calculate of these basic structure. And after prediction of the electrical behavior, this basic part, our simulator will get the result of whole device. So if meshing is very small, narrowing, then your prediction will be very good, very accurate value. If your meshing is large, then prediction is not very accurate value. So meshing is these things. Now I hope you have understand the meaning of meshing. Okay. So there is a format to writing meshing part is mesh space dot multi dot value. So value default value is 1. If you write default value 1, then okay, what machine you will define, that machine will be machine it will take from your code part. If you write the more than one value, that means you are writing narrowing part. Okay, so I will discuss the by one. I know you are not getting me very properly, but I will discuss when I will discuss about TFET code, then you will understand everything. Now this is the meshing part. Now I will give you an example. Here given x dot m equal to -1 is 0. So this is the way you have to write. Uh, Left it. I will discuss later. Now what is the meaning of meshing? I think you have understand. Now let's begin second part. We have to define reason and material. What is the format of defining reason? You have to write reason number, integer value, then what material you are using, then where what is the position of that reason. Okay, same thing here given. Reason number one, material equal to silicon, y maximum value, y minimum value. So one more thing, y maximum, y minimum, what is the x maximum, x minimum? Suppose you have device. This is the reason you want to define. So you want to define this whole region. So what is this value? This is x minimum. X minimum. What is this value? X maximum. And this is y minimum. This is y maximum. So in this way you can define in simulation trigger tool. Next, specifying electrodes. So suppose you have a MOS device. MOS device have source, have has drain, source, drain, and gate, as well as body. So these are the electrodes. 4 electrodes we have to define. So what is the way after writing electrodes? Electrode name here, right? Like gate, source, drain, whatever you want to write, right? And we have what is the position of the electrode value? Electrode name cathode, top, left, 2. So this is the basic thing, given basic example. I will discuss on TFET example. Okay. Now doping. What is the format of writing doping? Doping. What distribution type doping you want, like uniform doping or a Gaussian doping? It depends on you, or it depends upon the need of your device. Dopant type, a donor or receptor, what dopant you want, and what is the position of the what is the position where you want to doping. You have to write this thing like a doping uniform concentration value, n type, and reason. Okay. Position means already you have defined results, so only you have to write value. Okay. Now this is the theory part which is completed. Now I will discuss about the basic thing. What is the right? This is the references. Discard it, and let's discuss about code. Which code I want to show you. This is the basic TFET code, SOI TFET code. I want to give you. I want to simulate it in front of you. dig build. Let me open the dig build and let me extract that part. Now this is the code. Now here you can see same thing. First you have to write go at last. Okay. Now for before defining the meshing, you have to write mesh space multiple 2.2. You can write also one default value one. You can write two. So according to this, your mesh will change. Okay. So here we have to do. I have actually two-dimensional device. So we have only X mesh and Y mesh, not Z mesh. Z mesh only defined for three-dimensional value. So X mesh. So uh, what is the structure basically? In my case, I will tell you structure first. My structure is like this. This is the structure. What I am taking actually. This is this source, channel, drain. Here SiO2, SiO2, and here is subtract of silicon. Okay, this is 0, 0, minus 30 here. Now minus 30 to 0, 40. Now 70. Okay, this part is 10 nanometer or 15 nanometer. I will check there. Suppose 10 nanometer is whole here, silicon thickness. Now here 50 nanometer and now 10 nanometer. So this is our this is the structure which I want to simulate. Okay, so go to our that part. Now let's see once more. So here you can see meshing mesh started from minus 30. The space value is 0.001. Okay, this is called narrow meshing because this value is very less as compared to 0. So at the interface, what we are doing, narrow meshing doing. Okay, that's why it is narrowing at starting. Now X mesh, why, where is the interface? Share interface between air and device. That's why I have taken narrow meshing. You can take normal meshing, but it depends on you, don't worry. Now next part, minus 30 nanometer. Now 5 nanometer, after 5 nanometer it become minus 25. Here meshing is not very narrowing, 0.01. Like that we have to move till 0. 0 means what? Source channel interface. Here you can do at interface we are doing narrow meshing. Okay, till that we have to move t nanometer. T nanometer means what I have told you in my device structure. 30 nanometer source, 30 nanometer drain, and if a t 30 30 means how much? 60. Okay, so 20 nanometer or channel, not 20. Minus 30 we have started. So minus 30 to 80. So how much? 110 value. 110 value minus 30. Now 60, 30. So 50 nanometer channel. So we are considering 50 nanometer channel length, 30 nanometer source length, 30 nanometer drain length. Okay. So previously I told you I think 40 nanometer channel. So you can change that value 50 nanometer. Now same thing Y meshing. Y meshing started minus 2 nanometers. Why? Because we are adopting 2 nanometer of SOI site. Okay, SiO2 oxide. So minus 2 nanometer, then minus 1 nanometer. Here narrowing meshing. Why? Because there is an interface. Like that we have to move 17 nanometer. Okay. Now QTX dot mesh means where tunneling performance happening, where we are doing tunneling meshing, quantum tunneling meshing. So we know tunneling happening at source and channel junction. So 20 nanometer inside, 20 means upside, and minus 20 to 20 X mesh, and uh, what is 30 to 70 here drain side, and Y is 0 to 10 nanometers. This is quantum meshing. Now we have to define reason. So how you will define reason? Revision or not? Left it. Reason 1, we are source reason is given. Source reason minus 30 to 0 and Y 0 to 10. Silicon I am considering. Reason 2 means what? Channel reason 0 to 50 and 0 to 10 silicon. Okay. So this is the according to this we have defining reason. After simulating this code, we will get in front of you that thing. Now electrode. We are defining 3 electrode: drain, source, and gate. Electrode name equal to drain, that is number 1. X minimum. Drain means how much? Where from started? We have started electrode at drain means top side. Top side means thickness is 0, that means X minimum. Let me check. I will. Then you will understand. This is our structure. This is our structure basically. Drain. This is drain. Where we are defining code? Here. Electrode here. So here X thickness is 0, Y thickness is 0 to 10. Okay. And same electrode for source we are defining here. X thickness is 0, Y thickness 10. And gate electrode from here to here means X 0 to X 50, Y become 0. Means I am considering 0 thickness of electrode. Okay. Why I am considering 0 thickness of electrode? If I will consider thickness, so we have to define the metal value. Metal. What metal you want to define? Otherwise, only we can give the work function value. It will consider that value. Okay. That's why I am considering 0 value. Let's begin. So like this, you can see X minimum is 0 at T, and X maximum is at T, and Y minimum is 0 to 10. So in this way, we can define electrode. Now doping uniform we want, value source doping 10 to power 20, P-type doping in source region, N-type doping in channel region, value 1 into 15. This is the value pattern. Now contact, we have drain 1 neutral, and basically where which voltage we want to define, gate voltage. So that's why gate work function we have to take it 4.07. According to work function, this tool automatically consider the metal. What metal you have applied at the gate. You can change the work function. You can change accordingly your metal of gate metal. Okay. Now material silicon basically we are using. So we have to define silicon, material silicon. What is the effective mass of electron, effective mass of a hole? This is the ratio of rest mass of effective mass, like that, effective mass to rest mass. And this what models basically were CBT, SRH, band gap narrowing model, and band to band non-local milling model. This is the way you have to writing the model. So just copy paste. And why I am considering direct quantum direction one? If your tunneling happening in x direction, then quantum direction become 1. If tunneling happening y direction, in quantum direction is 0. It is predefined. So just remember this thing. No need to this is the just your comment value. No need to define, already we have to define. Now what method we have to use? Newton Raphson method. Here you can this value already defined, a carrier equal to 0, trap charge limit 15. You can change this value, then your value of the electrical parameter will automatically change. This is a predefined value. No need to change and no need to alter these value. Now after that we have to biasing part. Now this is the way to writing biasing part. Solve in it. First we have to drain biasing. Solve drain, zero value, almost zero value you have to give. Now we have to give we have to increase our drain voltage from till 1 volt. So first 0, then step size it is given 0.05, and final value 1, name is equal to 12. Okay, what voltage you want to apply, just change it. Now you can save any current value or any graph in log file. So this is a format writing log out here, your device name. You can alter it dot log. After the define gate value, gate biasing, solve v get 0, step size it is negative part is given. If you want to apply negative voltage to writing this part, otherwise only single one is enough. Why we have defined AC frequency? This is the frequency we have applied. Means a small signal we are applying as a gate voltage. That means that is the AC altered signal, AC signal, alternative current. That means small signal will amplify and it will give the larger value. So here our device we are using as amplifier. So if we are applying frequency parameter or frequency electrical signal, so then means we can create the capacitance at the junction. Okay, means if capacitance will occur, that means RF performance we can calculate. So for calculating RF performance, RF things, so that's why I'm applying AC frequency. If you will not apply frequency, then RF performance will you cannot predict, and only DC performance you can predict. So after applying this frequency value, you can predict RF performance as well. Now this output, what you want at output? Recombination band parameters, conduction band, valence band, mobility parameter, velocity, x direction velocity, y direction velocity, electron velocity means electron x direction, electron y direction, electron velocity, impact, flow line, current flow line, charge distribution, everything you can get at output. So just copy and paste in your code. No need to change that thing. Now you have to save your value, your data. This is a format to save out of your device name dot str, Tony plot your device name dot log, then your device name dot str. This is the way to save your data. Now you want to extract. So I want to extract only two value, threshold voltage and subthreshold swing. So this is the way you have to extract that value. So just copy and paste. Now this is the basic TFET code. So you just pause my video and understand everything one by one. Now I will run it. Before run, I will change the step size large, otherwise it will take time. Okay, no need to change and minus. Just let me. positive positive part. No need to check the negative part because it is just wasting time. Because my motto is to show you the result. So it is running. Wait for some time. I will skip that running part. Now we are going to finish our simulation. We will get results. Let's see what is the result value we are getting here. Now last voltage we get 1. This is the final gate voltage. Now let's check the result value. Now this is our plot we got, and here at extract part threshold voltage we have got 0.36 volt. And what is the subthreshold swing voltage? 0.04 volt per decade, or we can say 40.89 millivolt per decade. Good value, less than 60 volt. So we are getting both value good. Now we will check the 2D plot first. This is the structure which we have defined in our code, and we got this good structure. And here left side we got the drain current in linear format. We can change, go to display, change by scale log, and OK. This is the log current. Here off current we are getting 10 to minus 17, minus 16, in middle minus 17 and 16, 10 to power, very less value, but we should get. Now on current we are getting in between minus 10 per minus 6 to 10 per minus 7 ampere per micrometer. Now this is the our structure we are getting. So this is all about today lecture. Hope so you enjoyed this lecture and learn lots of things with this lecture. So keep tuned uh, with this channel, and you will get lots of video based on the coding. Like, share, and subscribe. Thank you.